Bismillah ar-Rahman ar-Rahim. So here we're working on the third tutorial which was posted this week. So on my course website I have the statement for tutorial number 3, and it's composed of 5 different exercises. So the first exercise is given an implementation of the size method for the singularly linked list class, assuming that we did not maintain size as an instance variable. So we have to come up with a method which is going to find the size of the list without using the size field that we've defined in the single linked list class. So I'm going to move over to my project in NetBeans, and here we're looking at tutorial number 3, question number 1. So now here's my size method. Obviously this is outside the singular linked list class. I'm just giving you a simple implementation without a test program. So we define a size variable, integer size equals 0. We define a node t, which is going to point to the head of some list. And we run a loop while t is not equal to null. I keep running it until t is no longer contains anything. It becomes null. So whenever you encounter a node, simply move ahead and increase the size by 1. Once the loop is finished, we have the size and we can simply go and return the size. So looking at the second question, implement a rotate method in the singularly linked list class which has semantics equal to remove first, and whatever node is removed, you have to add it at the end of the list. So the requirement is that you should not be creating any new node. So here the idea is that we have to first figure out where the first node is, and you have to remove this node. When this is detached, you would like to add this thing at the end of the list. So this way we can say that the first node went to the end of the list. If I repeat this thing for the next node, that would naturally go to the last of the list. Now, using this idea, we can simply say that this is rotate or rotation inside the list. Now, coming back to my NetBeans, here's my solution for question number 2. So what I did was I'm using the sorted dlist package that we've created in the class, and I'm using the dlist, which is the double linked list implementation, and the node implementation. Both of these are available in these 2 classes in this package, which we worked on during this week. So these 2 methods are outside the list, and obviously I'm passing the dlist itself as a parameter in the remove first method and the add last method. So let's first see how do we remove something from the list. Now naturally, remove first, as it states, we have to go and find the first node in the list and remove that. So we find node t, which is just a temporary reference pointed to the head of the list, and then we check if d.head is null, then return null, which means if the list is empty, we do not have to do anything, just return null. Otherwise, we're going to move the head to the next node. So the next node becomes a head. Once this is done, now what we have to do is reset the value of the previous pointer. So if d.head is not equal to null, means that the list is not empty anymore, then we have to say d.head.previous equals null. Because this is our understanding, head.previous is always null. So I'm just making sure that we reset these values. With regards to add last, so here we have dlist coming as a parameter, and the node which would have to be added to the end of the list. So what we do is we create a temporary reference, have it point to the end of the list, d.list. Now we have 2 cases here. If t equals null, which means the list happened to be empty, if that is the case, this means that all I have to do is just go and attach this thing in the beginning. So d.head equals d.tail equals the new node that has just come in, and we increment the size by 1. So if the list is not empty and we have something in the list, what we're going to say is n.previous equals stay, so initializing the values inside my incoming node n, n.next equals null, because this would have to be inserted at the end of the list. So naturally, this would be the tail, and tail.next is always null. T.next equals n, and d.tail equals n. So here's my tester program. I write a simple list. I insert 1, 2, 3, 4, 5 in there. I call the remove first method, so this is going to remove the first node. Notice I'm adding everything at the end of the list, which means it should appear as 1, 2, 3, 4, 5. So I use the node temp equals remove first d, so it'll go and remove the first node, which would be number 1, and add number 1 to the end of the list. So let's run the program. Let's see how it goes. There you go. So it was supposed to be 1, 2, 3, 4, 5. What it does is it removes number 1 from the beginning of the list and attaches it to the end. So moving on to the next question, describe an algorithm for concatenating two W linked lists L and M into a single list N that contains all the nodes of L followed by all the nodes of M. So there's a small misunderstanding over here. We're referring to W linked lists, and instead of saying into a single list, it should be saying into one W linked list N that contains all the nodes of L followed by all the nodes of M. So here we are. We have two lists. We have list L, which has 3 nodes in this scenario, and we have list M, which has 2 nodes in this scenario. So I'm looking at a very simplistic animation. What I do is I create a new list, which is empty right now, and I would like to have some pointers over here. So I would like to say n.head, or n points to the first node in L. So I'll be showing n.head equals L.head. I would like to say m.head equals L.tail, and L.tail equals m.head, and finally n.tail equals m.tail. So if I do something like this, that should be enough to have all of my links connected together so that n would function as an independent list. So looking at the solution for this, we have a method called concatlist. Again, I'm using the same class that we've written in our regular classes, sorted dlist2.dlist and nodes. I'm just referring to the same classes we've written in our regular meetings during the day. So I have a method called concatlist, which is passed 2 parameters, list L and M. And this method concats the 2 lists and returns a new list called the list. So we create a new empty list, dlist n equals new list. As I referred in the animation over there, n.head equals L.head. We make last node of L point to head of M and vice versa. So L.tail.next equals M.head. M.head.previous equals L.tail. We make list n.tail point to the tail of M, so n.tail equals m.tail. Once all these 4 pointers are connected, now we have to check or reset the size variable in the list n. So I can create a temporary node, have it point to the head of the list n. I run a loop which is going to find or traverse through the entire list. And I'm simply incrementing the size variable which is defined in the list n. So once the loop is done, I have traversed through the entire list, and it now contains updated value of size, which is equivalent to number of nodes in the list. And finally, we return n. So here's a small tester program. We create 2 lists, D1, D2. D1 contains 3 nodes, so I put 1, 2, 3 in there. The list contains 2 nodes, so we put 10 and 20 in there. I concatenate the 2 lists, so D1, D2 are passed to it, and a new list is formed called new L, and I here simply go and print the new L using or calling the toString method. So let's give it a run. Here we go. So first list was 1, 2, 3. Second list was 10 and 20. And as you can see, we have one list which is pointed to by new L, and it has concatenated the 2 lists together. So moving on to question number 4. Describe in detail how to swap 2 nodes, X and Y, not just their contents, in a doubly linked list L, given references only to nodes X and Y. Write method swap, which just takes 2 parameters, node X and node Y, and it swaps the 2 positions of these 2 nodes. And you have to write code in Java. So we'll look at our implementation. First, let's have a look at a very simple animation. So here's a solution. Obviously, there could be other solutions, but I'm looking at this particular solution. So we're going to assume that this is our list which is given to us, but we're not really sure where the head or tail is. So it would be better if you implement the swap method as part of the dlist class that we've written previously. So if this is implemented within the same class, we would not have to worry about the head or tail of the list. So here's a simple example. Let's say this is X and this is Y. So I'm going to create 4 pointers. I'm going to create previous to next pointer, previous to X pointer. So this is the node before X. Next to X pointer. This is the node after X. Previous to Y pointer, which is the node before Y. And next to Y pointer, which is the node after Y. So if I can have a pointer to each of these nodes, it would become very easy for me to change the values over here without having any problem of modifying the pointers within these nodes. So given this understanding, let's look at the solution. So here's my tester program, but before I look at the tester program, what I've done over here is I've extended the sorted dlist class, which is just an extended version of the doubly linked list class. The only difference here and our implementation in the class is that I've written the swap method. So I'm just scrolling down to get to show you the swap method. So here is the swap method. Obviously this is part of this class. So we pass it node X and node Y. Now first we have to check if the list is not empty or otherwise. So if one of these is null, we simply return nothing because we cannot swap if one of these is null. Now here we initialize the 4 pointers. So node next to X equals X.next. Node previous to X equals X.priv. Node next to Y equals Y.next. Node previous to Y equals Y.priv. Now we have 3 scenarios. Let's first look at the otherwise scenario, in which we simply go and make the swap. So detach X. How do we do this thing? We say X.previous equals previous to Y. Now remember, this is a node, or this is a reference pointing to the node before Y. X.next equals next to Y. So we're pointing to the node which is coming after Y, next of Y. Detach Y, so Y.previous equals previous to X, and Y.next equals next to X. So basically what we've done is we've swapped the positions of the pointers in X. So the previous and next pointers of X are copied on Y, and Y.previous and next are copied on X. Now what we have to do is reattach Y and reattach X. So we work with the node previous to x. So remember, previous to x was a node which was there before x. So we say previous dot x dot next equals y. And next to x, which is the node which was there after x, dot previous equals y. So basically we have swapped the position of x with y. Let's reattach x. So previous to y dot next equals x, and next to y dot previous equals x. So this is going to reattach and detach and reattach both x and y in the list. Now we could have some special cases. A special case in a sense that what if x is ahead? So if x is ahead, then I cannot say x dot previous equals something. That's going to crash my program. Naturally, x dot previous or head dot previous is always null. So in this scenario, there's a small change. All the code remains the same except this case. When instead of saying previous to x dot previous equals y, we say head equals y. So this is going to take care of this issue. The rest of the code remains the same. We also have a special case if y is the tail. So if y is the tail, again, all the code remains the same, except that we always know that tail.next is always going to be null. So in this case, the last line over here is declaring tail equals x, because next to y would be null. So this is going to take care of all of this. Now the issue is the code has become a little bit too long and there's repetition. Lots of code over here, at least these 8 lines, 7 of them are repeated in the 3 different scenarios. So what I've done is I've rewritten the swap improved method, and now the code looks a little bit too short compared to the previous implementation. So we go with the same 4 nodes, we detach x and detach y. Here's a special case. If x is head, then you attach it. Otherwise, the regular case. And next to x.priv stays the same. In case it was tail, if y was tail, then you go and change x to tail. Otherwise, just go and change that. So that's pretty much it. This is the code for swap. Now let's give it a test run. So in my test program, I'm calling this package extended sorted dlist because this is the one where I've put the swap method. Now we create a simple list D, run a loop, fill it up with numbers or values from 1 up to 10, 10 included. So we have 10 elements in my list. I go and print my list, and let's see if it works. So I'm going to detach 3 and swap it with 7. I'm calling the d.swap improved method with x and y, and we print the list. So let's see what happens. Okay, so first it simply goes and prints my original list, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now notice that what we were trying to do was swap the positions of 3 and 7. So you can see this has become 1, 2, 7, 4, 5, 6, 3. So 3 and 7 have changed position. So this was our first scenario when neither of these is head or tail. Let's see if we make this as 1, because 1 is supposed to be the head. Let's see what happens. Okay, there you go. So I'm swapping 1 and 7. So here you can see 7 has come to the head and 1 has gone and replaced the position of 7. Okay, let's test the other case. So I have 3 and I would like to swap it to 10. So this is the tail case, and there you go. So 3 is swapped with 10. Moving on to the last question. Describe in detail an algorithm for reversing a doubly linked list L using only a constant amount of additional space. Write method reverse that reverses all the contents in the list. So simply put, let's say my list contains 1, 2, 3, 4, 5. After I call the reverse method, and if I'm printing my list, it would be printing 5, 4, 3, 2, and 1. So let's figure out a way to do this. So here's a very simple solution. I do not need to create any additional methods in my list classes. So I create a new list and I fill it up with 10 values, of course, 1 to 10, and I print my list. Now what I do is I create a new list called V. I'm going to run a loop in reverse order. So starting from I equals 10, I is bigger than or equal to 1, I minus minus. Now, if you remember the implementation, we have the remove method. You have to pass it an integer value. The remove method goes and finds the node that contains this value and returns this node. But before returning, it will detach this node from the list. So when this node is detached, we can access it using node t. And I can add it. I can call the v.add method and pass it t. So it's going to go and attach it in the beginning of the list. That's pretty much it. So let's run the program. So here's my implementation, original list, and this is printing the list V, which is over here. So you can see everything over here is reserved or reversed. So there you go. This is a very simplistic solution to our tutorial number 3. Thank you for listening and see you inshallah next time.